Here's an overview of data integrity mechanisms typically used in embedded systems. A key term is Hamming distance, HD. Hamming distance is the smallest number of bit flips possibly undetected. This is a little bit tricky because you're usually interested in how many bit flips can you detect, and the Hamming distance is the number that are possibly undetected. So for example, if you want to detect all 1, 2, and 3-bit errors, the Hamming distance is not 3, the Hamming distance is 4, because the Hamming distance of 4 means there's at least one 4-bit error in the code word that is somehow undetectable. In general, the higher the Hamming distance, the better. The table on the right lists the types of codes that can give you various Hamming distances. Hamming distance of 1 you get for free, because Hamming distance of 1 means you're vulnerable to any number of bit flips. So that's the baseline, and the point of using an error code is to do better than HD1. Parity detects all single-bit errors. That gives you HD equal 2 because every 1-bit error can in fact be detected. Parity is computed by XORing all the bits in a data value together to produce the error code. You can do this either resulting in a single XOR bit, or you can XOR the bits in a bit position. So if you have a bunch of 8-bit bytes, you can XOR the 8-bit bytes together and get an 8-bit byte result where every bit is the XOR of all the bits in that bit position. That still ends up being a parity computation. It still gives you HD equals to 2. You can also do mirroring to get HD2, but this is a completely different way of handling it. Mirroring is simply you store the value twice, and you say, well, if one of them has a bit flip, the other won't. We won't know which one is right, which one is wrong, but we'll know they differ, so we'll know something bad happened. Typically, you're a little bit more sophisticated than that. Instead of storing the value twice, you store it once, and then you store it a second time with some computation performed, such as inverting all the bits. The reason for that is not about single event upsets, but rather if there's a software defect that wipes memory clean with a single value, for example, there's a loop that puts zeros where there shouldn't be any, and you store a 0 and all ones pair as the mirrored image, then it's less likely that the software will create a 0 in one byte and all ones in the next byte if it's just initializing memory. That does not increase the Hamming distance, but it's a good idea and certainly better than just storing the data twice and being vulnerable to a memory initialization loop. We'll get to CRCs momentarily, but there are some situations in which a CRC is only able to provide HD equals 2 as well. If you want HD to be 3, then you typically use a Hamming code, which is single error correction codes to correct single bit errors, some CRCs, or a short Fletcher checksum, and we'll get to Fletcher checksum in a moment. The idea at HD equals 3 is you have the ability to detect 1-bit errors and 2-bit errors, but you can spend the Hamming distance either to correct a single error or to detect both 1 and 2-bit errors. You cannot do both at the same time. To get Hamming distance 4, you need to use a CRC or a single error correction double error detection SecDed code. If you're using a CRC, typically you're using a Hamming distance of 4 to detect all 1, 2, and 3-bit errors in the code word and not detect all possible 4-bit errors. SecDed codes are a little more special. SecDed codes are codes specifically constructed to give you Hamming distance 4, but spending that HD equals 4 to be able to correct all possible 1-bit errors and also be able to guarantee detecting all 2-bit errors. Typically, a SecDed code is just a single error correction code with an extra parity bit that gives you that extra bit of Hamming distance. The size of a SecDed code is about log 2 of the number of bits plus 1. So they get expensive for really long data words, but for things like 32-bit words or 64-bit words that you would use in a memory store, they're actually quite practical and widely used in high-integrity computing. If you want a Hamming distance of 5 or more, you end up using a CRC, which we'll get to next.